I welcome you in this lecture. Today we'll discuss gyrator, which is basically a ferrite device, a ferrite based device. The other ferrite devices, as I said in the previous lecture, circulator, isolator will be discussed in the next lectures. So let us discuss gyrator. Gyrator basically is a two-port non-reciprocal ferrite device. So it has a really, let me try it. So this is how it should be. Port number 1 and port number 2. Port 1, port 2. So it has a relative phase shift of 180 degrees or pi radians. In the forward direction, and zero phase shift in the reverse direction, and zero phase shift in the reverse direction. So that means if a signal flows from port 1 to port 2 through this device, a phase shift of pi radians or 180 degrees occurs between the signals at port 2 and port 1. And if a signal now passes or is connected or is fed, for example, a signal is fed at port 2, the signal received at port 1 will be in phase, that is, there will be zero phase difference. Zero phase difference in the backward direction. So from port 2 to port 1, that's port 2 to port 1, there is zero phase difference. Now, as I said, it's a non-reciprocal device. Just to recapitulate this non-reciprocal, we have already discussed it, but let us once again try to recapitulate what a non-reciprocal device means. As you know, a non-reciprocal network or a device is one in which transmission of signal between any two ports, does not depend on the direction of propagation. That is, input and output ports are interchangeable. Now depend on the direction of propagation, or that's input and output ports are interchangeable. That means it's a reciprocal network. This is the case of a reciprocal network. A non-reciprocal network doesn't behave like this. So what I mean is that, say for example, I have a reciprocal network. This is port 1, this is port 2. For a reciprocal network, if I feed a signal, say for example at port 1 with amplitude A1 and phase theta 1, I receive, say for example, a signal with A2 amplitude and phase theta 1 plus phi, for example. Now what happens is that this is the input port, this is the output port, or port 1 is the input port, port 2 is the input port. So when I feed a signal of amplitude A1 and phase theta 1, for example, I receive a signal of amplitude A2 and phase theta 1 plus phi. Now to the same network, to this network, the same network, which is a reciprocal network, what happens is that if I feed, now this was port 1, this is port 2. Now if I feed a signal, the same signal, A1 theta 1 at port 2 or the output port, I will get the same output signal that I got in the first case. I'll get this theta 1 plus phi 1. So this means ports 1 and 2 are interchangeable. This is what a reciprocal network means. In terms of S parameters, if this is port 1 and this is port 2, in terms of S parameters, the condition is that S12 is same as S21. This is the condition for a reciprocal, two-port reciprocal network. Now, if we have a lossless reciprocal network, in case of a lossless network, lossless reciprocal network, I'm just trying to make you clear what a reciprocal network means. Now, if we have a lossless reciprocal network, a lossless reciprocal network would mean that if I have this as the input port and this as the output port, this is port number 1, port number 2. Lossless would mean I have a signal with amplitude A1, phase theta 1. At the output I'll be having a signal A1, phase theta 1 plus phi 1. So the amplitude of the signal remains the same. Such a network is called as lossless if the amplitude remains the same. For example, transmission lines are considered to be lossless as long as the amplitude remains the same. So just back to this gyrator or gyrator. It can be pronounced as a gyrator or a gyrator, so there is no problem in that. Now coming back to this, I said this is a non-reciprocal device. That means if I feed a signal at port 1, I received some signal at port 2 with the phase difference of pi radians. I have A1 theta 1, for example. I'll receive A1 at theta 1 plus pi radians or 180 degrees. So A1 amplitude remains the same. That means it is a lossless device. Lossless. Now phase changes. It was theta 1, now it is theta 1 plus phi. Now in the reverse direction from port 2 to port 1, there is no phase change, neither change in phase nor change in amplitude. So in forward direction 180 degree phase shift, in the backward direction there is zero phase shift. So it is a reciprocal, it is a non-reciprocal device, because in this case ports 1 and 2 cannot be interchanged. Now if I dig slightly a bit deeper into this reciprocal network in terms of S parameters, I said S12 is same as S21. So that would mean this is, for example, let me draw a reciprocal network. Is a two-port reciprocal network. For example, this is port number 1, this is port number 2. Let's assume that I have a signal A1 here, which is being fed at port 1. So the terminology that we used so far when we were discussing S parameters, we used A1, B1. A1 the incident, B1 the reflected. And at port 2 we used A2 incident, B2 the reflected. This is at port 2, this is at port 1. Now say for example, what it means is that S12 would be, for example, S12 would be B1 by S12 would be B1 by A2, assuming all the ports are matched. And S21 would be B2 by A1. So S21 would be B2 by A1. Now here this is B2 would be this direction. So the ratio of B2 by A1, this ratio, let me use a red color. So the ratio of this B2 and this A1, B2 by A1 is our S21, which is also called as forward gain. So the ratio of B2, I am feeding a signal at port 1, which is A1, and I receive something at port 2, which is B2. So the ratio B2 by A1 is equal to S21. Now what is S12? In case of S12, I'll redraw this circuit. Let us assume this is port 1, this is port 2. Now if I feed a signal here, let me use a green marker. If I feed a signal A2 here, I'll receive B1 here, assuming the ports are perfectly matched. There are no reflections at the ports. So what that means is S12 in this case would be B1 by A2. This B1 divided by A2. So if this ratio B2 by A1 is same as B1 by A2, so if B2 by A1 ratio is same as B1 by A2, that in other words means this gain is same as this gain. The forward gain and backward gain are equal. So that means S21 has to be same as S12 for a reciprocal network. Since a gyrator is ferrite based, basically it's a ferrite based device, and ferrites inherently are non-isotropic. As the properties of ferrites are different in different directions. So ferrites are non-isotropic. And isotropic, by the way, so far as isotropic materials are concerned, the properties of isotropic materials are same in all the directions. For example, if a wave passes through an isotropic medium, if it passes from port 1 to port 2 or port 2 to port 1, we'll be getting the similar result. That means the ratio of output to input or input to output, in this case the ratio of signal received at port 2 to the signal received at port 1 would be same as the ratio of the signal obtained at port 1 to that of port 2. In other words, for an isotropic material, S12 would be same as S21. So this is about non-reciprocal, reciprocal devices. Now let's discuss what a gyrator is. Gyrator. So let me paste a figure of a gyrator here. This is how it looks. This is the construction of a gyrator. Construction of a gyrator. Now, a gyrator, as can be seen from this figure, consists of a circular waveguide. This part from, let me use a red marker, from this spot to this spot it is a circular waveguide, and at the ends we have a rectangular waveguide, and at the other end we have again a rectangular waveguide. So we have a circular waveguide in the middle and rectangular waveguides at the ends. A circular waveguide, as can be seen here, so the circular waveguide part so far is concerned, let me use a yellow marker. So this yellow portion so far is concerned, this is the circular waveguide, and it is being tapered to form a rectangular waveguide at the end. And on the other hand, on the input side, we again have a rectangular waveguides. But the thing is that this rectangular waveguide is then bent and eventually connected to the circular waveguide. So all I'm saying is that, as can be seen, let me zoom it in. This part, as I said, is this part so far is concerned. This is a circular waveguide, and at the ends it is being modified into a rectangular waveguide. Again, here we are connecting it to a rectangular waveguide, but a but the rectangular waveguide is bent here and then connected to the circular waveguide. So if the cross section at this port 1 is like this, horizontal, here the cross section would be vertical. Here, as I said, the cross section would be here at this place it would be vertical. So from horizontal waveguide with a cross section horizontal, place it in horizontal at some distance, say for example at some distance L1, a shift, a tilt is being given to it, so it is being bent so that the cross section is in the vertical direction. So that's all I'm saying. So what happens because of this is, we'll understand that when we discuss the working principle of this gyrator. But before that, we need to discuss few things about the construction. So in the middle portion, in the circular waveguide portion, we have a ferrite rod as is shown. The ferrite rod is tapered at both ends. I'll show you the tapering. This is where the ferrite rod is tapered so as to avoid reflections from this ferrite rod. So this ferrite rod, so far is concerned, it is basically a circular rod tapered at the ends so as to avoid attenuation reflections from the sharp edges. And this is supported by a polyfoam. So this ferrite rod inside the circular waveguide is supported by a polyfoam, as can be understood from figure number 2. Say for example figure 2, this is the ferrite rod, this cross section is the ferrite rod, and it is being surrounded by, as you can see, it is being surrounded by foam or polyfoam, and then it's placed basically between north and south pole or between a permanent magnet. So permanent magnet is somewhere here. We have a permanent magnet here surrounding the circular waveguide. A permanent magnet could be surrounding this as I'm drawing it. This is where the permanent magnet lies, so as to create a constant magnetic field, static magnetic field, because a ferrite for its operation needs a static magnetic field. So let me erase it and then we'll discuss the working operation of this ferrite device, Gyrator. Okay, now that I have erased it, let us discuss the working principle or operation of this gyrator. So let us see what happens. We know the dominant mode for a rectangular waveguide is TE10. The dominant mode here is TE10. The dominant mode for a circular waveguide is TE11. And again here we have a rectangular waveguide, so the dominant wave mode would be TE10. So now what happens is that when a wave enters this port 1 with polarization as shown, vertical polarization, this is the electric field here at port 1. So what happens, the wave is vertically polarized or is polarized as shown here. The electric field is like this, as can be seen here in the figure, as shown by the arrows, by the dark arrows, for example here. So when this wave passes through this waveguide, say for example from point O to A, what happens, because of the tilt, the electric field rotates. Initially it was vertically up. Because of the tilting of the waveguide, the electric field shifts from vertical to horizontal direction, as can be understood from this figure. We have electric field vertically up. As we move away, as we move from point O to A, this keeps on moving, and eventually the field that comes out at A is in the horizontal direction, as indicated by this. Here, just before the curvature, we have the electric field vertical again. So it remains vertical up to some distance. But after this curvature, what happens, because of the 90-degree tilt, this tilt is 90-degree. As I said, initially the cross section is like this here. The cross section of the rectangular waveguide is like this. But as we move from point O to point A, what happens is that the cross section becomes vertical. So there is a 90-degree shift, 90-degree tilt of the electric field vector. So after this, the wave reaches the ferrite. When the wave reaches the ferrite, what ferrite does is that it further rotates it by 90 degrees. So the electric field vector, which was horizontal towards left here, now moves towards vertically downward direction, as is shown by this arrow. So it was initially here vertically upwards, then it moves in the horizontal direction because of the tilt in the waveguide. It shifts by 90 degree, and then it further shifts by another 90 degree. So as is shown here, as can be seen from this figure. So we have it vertically downwards. So from point A, for example, from point O, for example, point O to point, say for example, point C, we have a 180-degree phase shift. And after that, what happens is that wave reaches port 2 with vertically downward electric field vector. This is the direction this arrow shows. This green arrow shows the electric field that comes out from port 1. So at port 1 we have vertically upwards. Here at port 1 we have electric field which points vertically upwards, and at port 2 we have electric field which points vertically downwards. So there is a phase shift. This indicates that there is a phase shift of 180 degrees from port 1 to port 2. So let me erase it so that we can understand what happens to the wave when it comes from, or for example, when a wave is fed at port 2 and reaches port 1. Now say for example, a signal is being fed at port 2 with polarization as indicated, vertically upwards, as is indicated here. So we have a wave polarized vertically upwards at port 2. Now when this wave reaches this ferrite rod, the ferrite tilts it by 90 degrees in anti-clockwise direction. Anti-clockwise direction with respect to, say, some point P here on the axis of this device. If this is the axis, this blue line, if it indicates the axis, let's assume that there's a point P on it. So it tilts it by 90 degrees in the anti-clockwise direction. Now when the wave reaches this point, say for example point A, what happens is that this bend of the waveguide rotates it by 90 degrees, but this time in the clockwise direction. So the total shift, 90 degree caused by ferrite in anti-clockwise direction and 90 degree shift caused by the bend in the clockwise direction, nullifies each other, so that we get a wave which is polarized upwards. So we are feeding a signal which is polarized upwards at port 2, and we receive a signal which is polarized upwards at port 1. So there is a zero phase shift between the ports 2 and 1. So this can also be understood from figure number this. Say for example, this is figure 3. So we have a wave which is polarized vertically upwards. Here it reaches the ferrite, the polarization is settled vertically upwards. After it comes out from the ferrite, we have the electric field vector tilted by 90 degrees. And again, when it reaches the ferrite, when it reaches the bend here, as is indicated here, when it reaches the bend, let me use this marker. So when it reaches the bend, we have again 90 degree shift. So it becomes, because of this shift, it becomes again vertically polarized. So in the reverse direction, we have zero phase shift. In the forward direction, we have 180 degree phase shift. And that's what a gyrator is all about. And lastly, I can tell you the S matrix of a gyrator, since it is a two-port network. The S matrix of this gyrator is 2 cross 2, S11, S12, S21, S22. So assuming that the ports are matched, so that would mean S11 is 0 and S22 is 0. This is 0, this is 0. And so far as S12 is concerned, it will be 1, and S21 would be minus 1. So as I said, S12 is S12 is B1 upon A2 and S21 is B2 upon A1. So since there is a relative phase, this element is our S21. Since there is a relative phase difference of 180 degrees, that means this element has to be -1. And since there is, so far as the forward direction is concerned, that's S21, as I said, in the forward direction we have a phase difference of 180 degrees, so this element is -1. And in the other direction, our S12 so far is concerned, which is B1 by A2, should be equal to 1 because there is no phase difference in the backward direction. So that's all. S parameters, S matrix would be 0, 1, -1, 0 for a gyrator. That's all we have for the day. Good day.